Welcome to this episode of the SciX Now Learning Hub Introduction to LC-MS series. In this episode, we will talk about what affects mass resolution in time-of-flight instruments. We will first examine what factors can negatively impact mass resolution in time-of-flight mass spectrometers. Then we will discuss technical measures to address these challenges, ensuring that you can rely on excellent mass resolution in your instrument. Let's get back to the details of a time-of-flight experiment. In the previous episode, we have examined the ideal conditions. Now we will take a closer look at the real-world factors that have a negative impact on mass resolution. Ideally, ions of the same m/c start from exactly one point, receive exactly the same kinetic energy by the acceleration pulse, have therefore the same velocity, and arrive exactly the same time at the detector, resulting in one straight line in the detector signal. In reality, the ions show a spatial spread within the extraction region. As a consequence, ions further from the pusher receive less energy than the ions closer to it, resulting in ions with the same m/z, but different kinetic energies and therefore different velocities. They reach the detector at different times, which reduces mass resolution. In addition to the spatial spread, ions also bear an initial velocity, as indicated here by the length and direction of the arrows. This gives rise to a time spread which negatively influences mass resolution. Let's observe these two ions that start at the same distance from the pusher within the extraction region, but have different velocities. The time it takes to get the lower ion into the right direction, which is the flight tube, is called turnaround time. The ions with different initial velocities therefore enter the flight tube at different time points. They reach the detector at different times, which further contributes to reduced mass resolution. Next, we will learn about technical measures which improve mass resolution in time-of-flight mass spectrometry. Ions with identical m/z ratios, but differing in initial velocities and spatial distribution, can be brought into a more uniform state through a two-stage acceleration process. In this method, ions traverse two regions of increasing electric potential, instead of just one. This approach allows the ions to achieve a more uniform kinetic state, resulting in tighter energy distribution as they enter the flight tube. In consequence, they will reach the detector with a lower spatial spread, and therefore improved mass resolution than without the second acceleration region. In addition to the two-staged acceleration, the two reflector regions play a crucial role in enhancing mass resolution. Their function is to compensate for kinetic energy distribution. Let's review how it works with the help of this example with just one reflector. Here we observe three ions with the same m/z, but different velocities within the flight tube. When the ions enter the reflector, they run against an electrostatic field gradient, which acts just like an ion mirror. The gradient causes the ions to decelerate until being turned around. The penetration depth depends on their kinetic energy. Ions with higher kinetic energy penetrate further into the reflector before being returned. They take a longer path, and their arrival times at the detector are ideally the same as for slower ions of the same m/z with lower kinetic energy. This results in better resolution. Note that there is an angle between the flight tube and reflector that prevents returned ions from colliding with those entering the reflector. Furthermore, the reflector extends the flight path length, which additionally leads to improved resolution, without increasing the instrument size. Using two reflectors, as you can imagine, is even better than just one. In summary, the mass resolution can be compromised by the spatial and time spread of ions sharing the same m/c ratio within the accelerator. This spread leads to a variation in kinetic energy, resulting in differing velocities as the ions travel through the flight tube, which ultimately affects their arrival times at the detector. Then implementing a two-stage accelerator region reduces the spatial spread of ions with identical m/c within the accelerator region. Moreover, the two reflector regions effectively minimize the distribution of their kinetic energy of ions with the same m/c within the flight tube. The extended flight path due to the two reflector regions additionally improves mass resolution. Thank you for watching this episode. To view the full training course, including progress checks and a final quiz to earn a certificate, go to scieix.com. Log in today to take advantage of the highly rated training material offered in the SciEx Now Learning Hub. You can use the links below.